Here's an example of some of the types of questions that will be on quiz 5, again using our sort of key review material to go through all of those. We'll have these 3 key topics from the Intro to Kinetics set of slides, which was sort of 15B. Integrated rate laws and half-lives, what we covered on Monday in PowerPoint 16, and then reaction mechanisms on 17. So let's start with the first key idea we looked at was the definition of the reaction rate. So that's this somewhat unwieldy equation that reaction rate is defined in terms of the change in concentration, right? Remember concentration in molarity in those brackets over change in time. And we have to divide by the coefficient. So little c is the coefficient on the concentration of C. And if it's a reactant's concentration is going to be decreasing. Again, if we sort of drew a graph here, maybe we have a reactant A. This concentration is decreasing, so its rate of change, its slope here is negative. And so to make the overall reaction rate positive, we have to include a negative sign on any reactant. We can sort of summarize this unwieldy equation with this little shorthand. The overall reaction rate is the rate of any of our species X. So if it's C, it's the rate of change of C. That's what this term right here is. This is the rate. Just to highlight that, if we're thinking about C, this thing right here is the rate of C. And then the coefficient of C, of course, is our this thing here, right? The little c is the coefficient on C, and that's our coefficient that goes down here. So again, now that lets us, and again, reaction rate is just right here. So again, if we know the rate of change of any of the species, so if O3 is decreasing at 0.3 molars per second, we can use stoichiometry to determine the rate of change of O2. Again, just using the balanced chemical equations, so in this case 3O2. So we put 3 moles O2 on the top, 2 moles O3 on the bottom, and can quickly convert from O3 to O2. O2 is a product, so it is increasing, whereas O3 as a reactant is decreasing. Again, reaction rate, just plugging in for rate of X is rate of O3, so 0.3 molar per second O3. The coefficient on O3 is 2. So that goes down there as the coefficient there, and that gets us 0.15 molar per second as the reaction rate. Remember, that's the same no matter what species you use. So again, if we wanted to use O2 here, we could do 0.45 molar per second of O2 and divide by, since O2 has a coefficient of 3, divide by that by 3, it gets us our same 0.15 molar per second for the reaction. Okay, here's a new example of this. We have this nice reaction. NO2 goes to N2 plus O2, and O2 is being produced at 0.0022 molars per second. So the reaction rate, we'll use that key equation. Go back to black here. Rate is equal to, in this case, the rate of, we have O2, so rate of O2, absolute value divided by the coefficient of O2, which in this case is 0.0022 molar per second, and the coefficient is 2. Divide that by 2, and we get 0.0011 molar per second. So this is really just good stoichiometry review, not hard questions at all here. Consumption of NO2. NO2 is a reactant. I would say it's being consumed at a rate of, well, let's look. O2 is being produced at 0.0022 molars per second, so we can either use this equation or just use the relationship between the two reactants there. I'll use this equation again, maybe just to give an example. Here, rate is equal to absolute value of the rate of NO2 over the coefficient of NO2. And again, here, now we know the rate. So when we plug in, we would get 0.0011 molar per second is equal to the rate of NO2 that we're looking for over the coefficient on NO2 is 2. So we just have to multiply both sides by 2. 2 by 0.0011 molar per second is equal to 0.0022 molar per second of NO2. I've dropped the absolute value here. NO2 is being consumed. its rate of change would be negative if we wanted to know the rate of change. So delta NO2 over delta T would be equal to negative 0.022. But I'm interpreting the consumption there as incorporating that negative sign. Okay, for rate of production of N2, now for this one we can look at doing it in either the same way we did B, or we can do it using the stoichiometry case that we did here, right? We're always allowed to just use these coefficients here. I'll just show that using the coefficients, so we'll do that. We can take 0.0022 molar per second of O2 and multiply that by, in this case, O2 is what we have, and the coefficient there is 2, just using the balanced chemical equation, but 2 there, so we need to put 2O2 on the bottom. And the coefficient on N2, what we want on the top, is just 1 mole of O2, or sorry, 1 mole of N2. So 0.0022 molar per second of O2 times 1 over 2 gives us 0.0011 molar per second of N2. So again, these are not difficult, but definitely remember to actually know this sort of key equation here and how to apply it to your particular problem. Pay attention to whether things are reactants or products. Reactants are consumed, therefore their rate of change is negative. Products are produced, so their rate of change is positive, right? If we wanted to know the rate of change of N2, that would just still be positive because it is a product, and so it's being produced. Okay, let's look at our next example here. Now we're getting into a new sort of idea. We're drawing a reaction coordinate diagram. So this is really goes along with our simple collision theory ideas. So that's the next key topic. Let's look at that. So a reaction coordinate diagram goes along with simple collision theory. For a reaction to occur, reactants must collide with enough energy and in the correct orientation. The key thing the energy reaction coordinate diagram will show us is it will show us reactants, products, their relative energies, and it will show us that key energy, that activation energy, E sub A, which is a key determinant of the reaction rate. The bigger the activation energy, the more energy we need to clear to get from reactants to products, the slower our reaction is going to be, because fewer particles will have enough energy to get over that barrier. So let's look at what our reaction coordinate diagram looks like using our example. So the reaction is exothermic. That means heat is released, which means our products are going to be lower in energy. Remember, we're thinking about sort of reactants going to products. And so that's what our reaction coordinate diagram is showing, with energy on the y-axis, a reaction progress on the x-axis. And if we start with reactants, which I'll represent with R, we go to products, which I'll denote with P. Then the key point on that path from reactants to products is the transition state, where we have that maximum energy state on the way from reactants to products. We can label that with the activation energy, which is this energy right here, from the energy of the reactants all the way up to the energy of the transition state. So that's our activation energy, E sub A. When a catalyst is added, the reaction proceeds faster, so we can add a dashed line to show that. I'll do that maybe in red here. So when a catalyst is added, what does that do to the reaction? The key thing that catalyst does that you need to remember is that it lowers the activation energy. So again, on our key summary slide here, adding a catalyst, it's going to increase the fraction of collisions with enough energy. So it's going to affect this energy criteria, and because it lowers the activation energy. So with a lower activation energy, the same collisions will now get over the barrier that wouldn't have before. So that's the idea. We can draw a new pathway. So this is basically my E dashed line. The activation energy is lower, and that's going to increase my reaction rate. Okay, so there's my explanation. 5a, another just example. So according to simple collision theory, what three things must happen for a reaction to occur? Definitely something that you should memorize for the quiz or exam. Particles must collide with enough energy and the correct orientation. So that's, again, right off of our key summary slide. What factor explains the importance of this? Well, when we increase the concentrations, this is going to increase the number of collisions. If I go from having, say, one black particle and one white particle in my container, those will collide on average a certain number of times per second. If I increase the concentrations, now there's many more possible, in this case roughly 4 times as many possible collisions, so that increase in collisions will increase the rate of my reaction. So in this case, factor number 1. Okay, our next factor is the Arrhenius equation. So this comes out of simple collision theory, but this is the first sort of more complex mathematical component on this exam. So the key thing you need to know are you need to be able to identify these 2 key equations and what all these variables mean. K should be familiar from the previous example or from the previous quiz as our rate constant. That's what K is. A has the slightly odd name of pre-exponential factor. Okay, so what does that mean? It's basically just summarizes the effect of all those other parts of simple collision theory. It combines the number of collisions per second plus the correct orientation, all that kind of stuff together into one key factor. An important thing to note here is that it has the same units as K, because this last term here is unitless. This last term in the equation has an important conceptual meaning. This is that fraction of collisions that has enough energy to lead to a reaction. So this term here, how many collisions have enough energy? It's this fraction. This is always a number that's less than or equal to 1. The bigger the activation energy, the fewer collisions actually do have enough energy to clear the barrier. So that's what this term summarizes. It depends on the temperature T, which has to be in Kelvin. R is our gas constant, which will be given to you on the quiz. You can just look it up, 8.314 joules per mole Kelvin. And EA, again, is our activation energy. That's that key parameter. Not a ton of room on this slide here, but I'll put it down here. EA, again, has units of joules per mole or kilojoules per mole. We have the second version of this equation, which is just the same equation, but taking the natural log of both sides. This is going to be how we make an Arrhenius plot, where we can look at this equation and compare it to the equation of a line, y equals mx plus b, and use that to determine the activation energy for a reaction. So important to know the Arrhenius equation and not confuse it with all of our other equations that have like a little t in them or a in brackets for concentration. Okay, let's see what that looks like now doing the problem on it. So the rate constant K for the decomposition of hydrogen peroxide was measured at different temperatures. What's the activation energy of the reaction? Okay, so in this case, we're measuring the rate constant K at different temperatures. And then you look at what we're plotting. It's ln of K versus 1 over T. This is called the Arrhenius plot. And we can see the equation that corresponds to it, right? It's that same linearized equation that we looked at on the previous slide. This one right here. So that's our equation that has ln of K and 1 over T in it. And now if we compare that equation to the equation of the line, we can use that to determine the activation energy. So we just take that equation. ln K is equal to negative EA over R, 1 over T plus ln of A. Again, this A is the pre-exponential factor, not the concentration of a reactant. We compare that to y equals mx plus b, what we did before break on that handout. And we can see if we line everything up, negative EA over R is in the position of the slope m, 1 over T is our x variable, ln of K is our y variable, and natural log of A is equal to our y-intercept. So again, we can just use this relationship to say negative EA over R is equal to m. Again, when we look at this, y equals mx plus b, we have here that m is equal to, from the plot here, negative 6,700. That we plug in for the slope m. What are the units on the slope? Remember that the units here R for slope, it's going to be the y unit over the x unit, because slope is that sort of rise over run, so delta y over delta x. And so here the y unit is unitless. When we take a natural log, that's always unitless. So the y unit has units of 1. The x unit has units of Kelvin to the minus 1. 1 over Kelvin to the minus 1 is equal to Kelvin. So our units here are negative 6,700 Kelvin. And that's equal to negative EA over R. To solve for EA, we have a negative on both sides, so we can cancel that. And we can say EA is equal to then get EA by itself, we'll multiply both sides by R. So 6,700 Kelvin times our R, which is again off of the equation sheet here, 8.314 joules per mole Kelvin. And that will cancel everything nicely for us. Kelvin will cancel, and we'll get into the correct units of joules per mole. The final answer is equal to 55,700 joules per mole, which if we divide by 1,000 to convert from joules to kilojoules, this would be 55.7 kilojoules per mole. A good check is that your number of kilojoules per mole for activation energy should always be in sort of the 10 to 200 kilojoules per mole type region. Hard to have an activation energy much outside of that range. That's a pretty large range. So yeah, that's again really going back with our comparing everything to a line, which is a main theme in this quiz and on this part of the exam. Okay, the next key area of content to cover is integrated rate laws. There's a lot of different variations of problems on integrated rate laws, but it all just comes down to applying the correct equation, right? The key thing you need to memorize here is just this little bit of memorization. 0th order is A versus T, 1st order is ln of A versus T, and 2nd order is 1 over A versus T. So if you can memorize that little bit, you can then determine everything else that you need to know just from applying the key rules and principles. So if it's A versus T, you want to look for the integrated rate law with A in it, and the half-life also with A not on top, right? A in it. 1 over A, you're looking for things that have 1 over A in the half-life and 1 over A in the equation up here. So yeah, memorize this one line of the table and then just apply what you need to know from there. Let's then get to some examples. Again, lots of equations, but all just applying that little bit of knowledge here. So we're going to look at the first order decay of this carbon-14 radioactive dating. Okay, our first job then is to determine what equations we need to apply in this situation. So we are just given that it's a first order process. That's really useful because it means we need to use the equations that are basically ln of A versus T. So those are all the equations that we could possibly use. Maybe we'll just highlight those to start with. So ln of A versus T, that's this one. It's also this equation here, the sort of ratio form, which only applies for first order. And we could see that we do have a half-life, right? This is that T 1/2 variable, so that could be useful. In this case, since we have a half-life, we may as well highlight that equation too. We can go between half-life and rate constant using this equation. Remember that 0.693 is ln of 2, so this is the half-life that has ln of 2 in it. These are all apply to first order processes. Don't try to apply these types of equations, right? This is what we did previously, Arrhenius equation. Even though it also has a T, but a capital T and an A in it, these are just a completely different sort of phenomenon. This equation here does also apply to first order, just a slightly different way of writing it. Okay, so with that equation chosen, now we want to determine the time, right? So how old is the sphere, right? That's our key question. We want to know how much time has passed since the sphere started decaying. It has 5.6% remaining. So this is always one where I would encourage you to use this ratio form. Since we're trying to solve for t, this will make it particularly easy. So we can plug into this equation, ln of A over A naught is equal to minus kt. Now we're going to solve for t, so we can just divide both sides by negative k. That will get our t on its own here. So we have ln a over a naught over negative k is equal to t, which is what we're going to plug into. Now, to plug in here, we sort of need a trick here. We don't know a or a naught, but we do know there's 5.6% of the initial 14 carbon remaining. So the trick we can use there is we can say the initial amount, which is sort of A0, right? This is how much was present at t equals 0 when the decay started. Since all we know is the percentages, we'll say that initial is 100%, and it's 5.6 remaining, so that is how much is left. Basically, about 95% of it has already decayed. There's 5.6% left, so A is equal to 5.6%. Then we can plug those in and solve. One sort of caveat here is that we don't actually know K yet, so that will let us know these two that we can plug in. But we don't know K yet. We can solve for it, though, by using our half-life equation. So we have this equation. So we know T1/2 is equal to 0.693 over K. So since we know the half-life, we can solve for K. If we multiply by K and divide by T1/2, these variables can sort of change places, and we get K is 0.693 over T1/2. which is 0.693 over 5730 years. That will give us our K. I'll plug that in down here. K is equal to, and you can see our units here. This is unitless. Years is on the bottom, so we have years to the minus first for K. So I get 1.21 times 10 to the minus 4 for K. Again, we can always go back and forth between half-life and rate constant using this equation. Now we're in good shape here to just plug in and solve. So we have, I'll do that down below here, ln of A is 5.6, A naught is 100, over negative 1.21 times 10 to the minus 4, year to the minus 1, is equal to t. When I get that and I round it to just 2 sig figs, since we only have 2 sig figs here, I get 24,000 years. Again, years to the minus first and the bottom here, so that brings years up to the top. Time is always going to be in units of years. So a nice example there using sort of all the different types of equations that we have to use, a half-life and an integrated rate law together. The next step, which graph would be linear? Well, since it's first order, that means ln versus t has to be linear, so nice and simple. What is the value of the rate constant, including units? Well, we solve for that back here. So in this case, k is equal to 1.21 times 10 to the minus 4 years to the minus 1, or 1 over years if you prefer for the unit there. So yeah, once you know the order, generally it's, just plug into the appropriate spot. Remember this trick that only applies for first order processes where you don't actually need to know the concentrations in molarity, you just need to know the relative percentages. Okay, here's another example. We have this decomposition and we've made these 3 plots. We want to know the order, rate constant, and the rate law. So in this case, the order of the reaction, well, we can go look at the graph here. So in this case, we find that the order of the reaction, since ln versus di is linear, so we have ln di versus t is linear. We've identified the linear plot. Since that's linear, that means it must be first order kinetics, right? Remember, that's the key thing to memorize. 0th is a, first ln of a, second is 1 over a. What are the units of the rate constant? In this case, when we take the natural log up here, there's no units on the y-axis here, so the units up here are 1 or unitless. On the x-axis, we have seconds. K, remember here, the slope, m, is equal to negative k. If we look at the key equation here, it's ln of a is equal to minus kt plus ln of a0. So negative k goes in the position of the slope there, so the slope here is equal to negative k. And so the slope has units of, and again, the units of the slope here, which are rise over run. Again, something that will come up again and again on this sort of exam, y unit over x unit. So this is 1 over seconds is our units there. And I mean, again, this is on our sheet. You certainly can memorize it if you want, but you don't really need to. Yeah, every time we increase the order by 1, we get 1 more molarity in the denominator. You certainly can if you want to memorize these, but you can also just get it right off of the graph or from the half-life equation too if you desire. Okay, write the rate law for the reaction. That's just a nice application to this top part here. Since it's first order, the power here in the rate law is 1. So the rate law in this case is rate equals K concentration of dye. And then again, the power is first because it's first order. And anything to the first power is itself. So we can just write it as K times the concentration of dye. All right. Again, the one thing I guess we didn't do in this example problem is use the slope here. Remember, that's a very important thing to be able to do. If we had that the equation for this line was negative 0.12x plus 0.02, let's say that's our equation of the line, well, then that means that since our slope here is negative 0.12, that means that K is equal to negative the slope. So the K is equal to 0.12, and then the units are 1 over seconds. Notice that for all 3 of these, the slope comes out basically related to the K. So if we look at each of these here, in this case we have slope is equal to negative K. In this case we have slope is equal to negative K. And in this case we have slope is equal to K. So in all 3 cases, once you apply the equation, take the slope and make it a positive number, and that will be your rate constant. So that's a nice commonality between all 3 of these equations. Okay, the next step here is reaction mechanisms. So how does a reaction work at the molecular level? By these series of elementary steps. Remember, the steps always have to add to your overall reaction. You can sort of cancel things in common as reactants and products. Those elementary steps are important because they represent a single sort of collision, and therefore we can write their rate law using collision theory. So for a unimolecular step like A goes to products, the rate for that step is K times A. For a bimolecular step, it's K times A times B, because these are the 2 things that collide. For a termomolecular step, KABC. Again, we had on the slide some special cases, right? If it's 2A goes to B or something like that is our step, then the rate law for that step would be like rate equals K A squared. Again, because 2A is really A plus A colliding goes to B. This is the one case where we can just use the coefficients, in this case 1A and 1B colliding, to give the orders in the rate law. Only works for elementary steps. In the course of our reactions, we might have these reaction intermediates, things that are formed as a product in an early step and then later used up as a reactant in a later step. These can be used to help us eliminate potential mechanisms. If we detect an intermediate that's not predicted by the mechanism, that completely rules out that possible mechanism. On the other hand, the reverse case does not apply because we might just not be able to detect the intermediate. So finding an intermediate provides you evidence against certain theories. It doesn't prove any one mechanism over the other. Catalysts work in the same way, but those we add to the reaction mixture at the beginning, and so they're going to be used as a reactant in an early step and then be regenerated as a product in a later step. So similar to intermediate, but pretty different conceptually. Okay, so let's use that first little bit of key information to start doing our practice problems. Here we have some rate laws and need to determine the elementary, the molecularity. So here, since it's Ka, that means it must be a unimolecular step. So this must be something like A goes to products, just a single thing colliding. The second one, the order is 2, so that must be a bimolecular step. The third one it's a Ka squared, so this is like that example I showed, A plus A goes to products. This is also bimolecular, it's two things colliding. And similarly for D, A squared times B, that must be termolecular. This is like 2A plus B goes to products is what that step is describing. Okay, here's another piece of this. We have this particular reaction mechanism. The first thing we can do is add all up our steps to get the overall reaction. In this case, we have the formation of CH3 plus in step 1, then it's consumed in step 2. So since this is formed in step 1 and then consumed in step 2, that means CH3 plus has to be our intermediate. The overall balanced reaction, well, everything else doesn't cancel, so CH3Br plus OH minus goes to CH3OH plus Br minus. Okay, now we get to part 3. What experimental rate law would be consistent with this mechanism? That means we need to use this second key piece of information from that sort of set of slides. The steps have to add up to the overall mechanism. We did that previously. Now, the rate law predicted by the mechanism must agree with the experiment. We can always use this first key idea, that the slow step determines the overall reaction rate. So rate is equal to the rate of the rate determining step. Steps 2 and 3 usually apply if we have sort of a fast equilibrium step, like A plus B goes to C, and then C plus D does something else later. Steps 2 and 3 are really important for the exam, but they're not on this quiz, so I'll show the example, what we get from just step 1 of this process here shown below. So the idea here is that we can write the rate of each step using simple collision theory. Because step 1 is unimolecular, the rate of step 1 is equal to K1 times CH3Br. Because it's just a single CH3Br that's sort of falling apart or breaking there. The rate of step 2, if we needed it, would be equal to K2 times CH3 plus times OH minus. So in this case, what experimental rate law would be consistent with the mechanism? Well, the overall rate of the reaction is going to be equal to the rate of the rate determining step. That's the slow step, or step 1 in this case. So we can say that the overall rate of the reaction is equal to the rate of step 1, which is equal to K1 times CH3Br. And in this case, CH3Br, we do need to know step number 2 here. We must eliminate any intermediates if they are present in the predicted rate law. But in this case, we don't have any. CH3Br is a reactant, so this is the rate law that would be predicted by this mechanism. Now, for the exam, you'll also need to be able to do this part number 3 here. We'll cover that in class Friday, and again, do some more examples of that, maybe even on Monday when we're reviewing for the exam. So for the quiz Friday, you just need to be able to sort of get through this first part, but this is also included there for reference. So yeah, good luck, and please stop by office hours or send an email if you've got any questions.